This section looks at inverse functions. So let's remember what a function is, or what the definition of a function is, and then we're going to talk about the definition of a one-to-one function and then how inverses are found. So recall that we said before that a relation is a function if and only if each value in the domain corresponds with exactly one value in the range. And what we meant by that was every time the number appeared, it should be associated to the same y value it had before. Graphically, we said that a relation was a function if it passed that vertical line test. So let's remember how to do that. Well, let's determine if the following relations are functions by using the vertical line test. So what I would do is I would draw that vertical line. If I intersected in more than one place, then I wasn't a function. Well, for example 1, I've only intersected each time I've drawn a vertical line in one place, so yes, I am a function. What about example 2? Well, if I draw a vertical line on example 2, I intersect in 2 places. This was not a function. What about example 3? Example 3, just like example 1, any vertical line that I draw on here will only intersect at most one place, which meant yes, I was a function. So again, remember, the definition of a function is that every time that x value appeared, it was associated with the same y value. Well, now we want to talk about one-to-one functions. A one-to-one function is a function, so it's already a function, it already passes that vertical line test, where every value of y corresponds to only one value of x. So here you think of it as if your y value repeats, it's always associated with the same x value it was before. So this time, we already know we're a function. We already know that each x only corresponds to one y, but now each y has to correspond to one x, so 1 to 1. So you can only have distinct ordered pairs. So let's take a look at the left-hand side here. I have a function. Here's my domain on the left, and here's my range on the right. Is this function 1 to 1? Well, let's take a look. I'm not sure. What I said is if you have a y value that repeats, it's always associated with the same x. Well, do I have any y values that repeat here? No, I don't. So 1, 2. 1 is associated to 2, 2 is associated to 4, 3 with 6, and -1 with -2. So is this function 1 to 1? Yes, because none of the y values repeat. What about the function on the right? Is this function 1 to 1? Well, again, let's take a look. Do I have any repeating y values? I do. I have a y value of 1 twice. Well, what x values is it associated with? Well, here I have the ordered pair of 1, 1, and on the bottom I have the ordered pair of -1, 1. Are these x values the same? No, they're not the same, so that means that this function is not 1 to 1. So, again, a function is 1 to 1 if every y corresponds to only one x value. But here we noticed we had a repeating y value that didn't have the same x value. So this function is not 1 to 1. Well, just like with determining if a relation is a function, we can use a line test to determine if a function is 1 to 1. We use the horizontal line test. The horizontal line test says the following. If you can draw a horizontal line that's going to cross the graph of the function at most one place, then the function is 1 to 1. So let's take a look at the following 3 functions, examples 4, 5, and 6, and determine if these functions are 1 to 1. Well, each one of these are functions. They would pass the vertical line test, but now we need to know, are they 1 to 1? Well, how do you determine that? You draw a horizontal line. So let's take a look here. Here, I intersected this function in 2 places. Because I intersected the function in 2 places, you can see that my y value of, let's call it 3, is associated with 2 different points, or 2 different x values. So this is not 1 to 1. It failed my horizontal line test. What about example 5? Well, every horizontal line that I'm drawing here is going to intersect this blue line in only one spot. So this is, yes, 1 to 1. What about my last one, example 6? Well, again, if I draw these horizontal lines, the most I'm intersecting is in one spot, so yes, I'm also one-to-one. So a function is one-to-one if the y's only correspond to one x, and we can use the horizontal line test to determine if a function is one-to-one. Well, why does that matter? Why do we care whether or not we are one-to-one? Well, the reason for that is only one-to-one functions have inverses. So the only functions that have inverses are one-to-one function. So how do you determine if functions are inverses? The functions f of x and g of x are inverses of each other if you can compose f with g and get a result of x, and if you can compose g with f and get the result of x. So two functions are said to be inverses of each other if f of g of x is equal to x and g of f of x is equal to x. So let's determine if the next three examples are inverses of each other. Let's start with example 7. So I'm given that f of x is equal 2 to the x and that g of x is equal x over 2. Let's determine if these functions are inverses of each other. To do that, I need to first find f of g of x. If the answer to this is x, then I find g of f of x. If both of those are x's, then we're inverses of each other. So let's go ahead and start. So this again meant to replace all the x's in my f of x with g of x. So I write 2, and then instead of writing this x, I write what g of x is equal to, and that's x over 2. Well, if I clean this up, my 2's will cancel here, and I'm just left with x. So far, so good. Now I need to find g of f of x. If this is equal to x, then my functions are inverses of each other. Well, remember, g of f of x means everywhere there's an x in my g of x, replace it with f of x. So if I'm writing, instead of this x in my g of x, I would write 2x divided by 2. Well, if I clean this up, g of f of x is just equal to x. So g of f of x is equal to x, and f of f of x is equal to x. So because they're both equal to x, we say that yes, the functions are inverses of each other. What about example 8? Well, same thing. Here's your f of x, and here's your g of x. So find the composition. Let's start with f of g of x. Again, this means everywhere there's an x in your f of x, replace it with g of x. So I would write 1/4 instead of my x. I write what g of x is, and that is the 4x minus 20, and then I need to finish off with my minus 5. Let's clean this up. So f of g of x is equal to, if I distribute my 1/4, a fourth of 4 is just x, a fourth of 20 is minus 5, minus 5. If I continue to clean this up, I get that f of g of x is x minus 10. Is this x? No, this is not just x, so I can stop here. I don't need to find g of f of x because the only way that two functions are inverses of each other is if both of them equal x. So because this is not just x, I can stop right now. They are not inverses. Let's look at example 9. Again, here is my f of x, and here is my g of x. Start by finding f of g of x. So I say the cubed root of, instead of writing x, I write what g of x is equal to, and that's x cubed minus 5, and then I finish off with my plus 5. Well, let's clean this up. Well, minus 5 plus 5 will cancel, and I just have the cubed root of x cubed. Well, the cubed root and the cube will cancel, and f of g of x is just equal to x. Great, I'm halfway there. Now I just have to prove that g of f of x is also equal to x. So let's find g of f of x. So I would write, instead of this x, I'd write what f of x is equal to, and that is the cubed root of x plus 5, but I need to cube it and subtract 5. Well, the cube root and the cube will cancel, and I'm just left with my x plus 5 minus 5. Well, my plus 5 and minus 5 will cancel, and then I'm just left with x. So now both f of g of x and g of f of x are just x, which means that yes, my functions are inverses of each other. The next video is going to deal with how to find the inverse of a function and graphing both of them on the same coordinate system.